Okay, so the last video was kind of how to plot a parabola the hard way. Let's look at how to plot a parabola an easy way, and I'm going to kind of do this in several steps. Modify and make the code a little bit better in several steps. So I'm going to look at this down here. All that I have up here is just a copy and paste of what I have. Like this so far is what I have up here. And to do what I want to do first, I'm going to use a library called Numpy. So I'm going to say import Numpy as in P. Okay, so now Numpy is going to be similar to the matplotlib. Numpy is a library that's used a lot for like data science and that sort of thing, but it's a very good sort of vector/linear algebra library. So how can we use it here? Well, the first thing that we're going to do, we're going to come down here, and instead of just making a regular Python array, I'm going to say np.array and give something like this. Okay, so now x is now not just a normal array, it's a NumPy array, which means we can do a lot of new interesting things to it. So let me just run this code. Nothing should change other than I'm doing this import statement. But the plot that we're going to get here should look exactly like this plot. So I'm going to run the code, and again, this is what we get. It's the exact same thing. Okay, so now what I want to do, one of the things that we can do with NumPy, with a NumPy array, we can actually like square the array. So I want to do y is equal to x squared. So I'm gonna delete that, and I'm going to do x star star 2. Okay, so what this means. Okay, x is an array, and when you do something like this, it does things element-wise. So y is going to take y is going to be x squared, is going to take this array here and raise every entry to the power of 2. It's going to square every entry. Okay, and so now this is obviously, I made some mistakes up here in the squares, so this already is a big improvement. I'm not actually going to have to square each thing by myself or by hand. The computer is going to do that for me, which again is what we want computers to do. So when I run it, the picture should be exactly the same. It should not change at all. Okay, and again, this is exactly what I get. Okay, so now let's see what happens. Now it's very easy. If I want to do, say, y equals x cubed, I can do something like this. I'm going to run it again. I get cubed. Okay, so let's say I want to do this plus x squared. I'm going to run it again, and I get this. Okay, now let's say I want to do sine of x. So let's say I want to do y is equal to sine of x from -2 to 2. Maybe I'll just write sine of x here. Okay, and make a prediction about what you think might happen. Okay, so here's a problem. There is no sign defined. Okay, so this function, sin, this is not a function that just is defined that Python has access to. It's a function in a number of places, but it's also a function in the NumPy library. So if I want to use sine, I need to do np.sine. And so what this says is telling Python to look in the NumPy library, which we've imported, and now we're going to look in that set of functions that we have and find the sine function and now do that function. Okay, so now we're going to run this and we should get a good sine plot. All right, so there we have a good sine plot. But let's say we want to sort of make the period so that we want to do sine of pi x so that we get the a different period, right? So that we get a whole period, or I guess 2 periods. So this is going to be pi. Okay, pi is pi. So let's see what happens when we run this code. All right, so now pi is not defined. Okay, so pi is actually a constant defined in NumPy. So we can do np.pi, and we run this code. And so now we have this. Okay, so why does it look all jaggedy like this? Well, it looks jaggedy because, again, it's just plotting at these various sample points and doing the lines in between. So this like interpolates the sine function at this point, this point, this point, this point, this point, and this point. Okay, well, now the obvious question is there, I mean, I don't want to have to come back here. I mean, maybe if I had, sample point every 0.1, I would have something that worked out well. But do I really want to do, 0.2, minus 1.9, minus 1.8, minus 1.7, and so on and so forth? Or is there a programmatic way to do this that doesn't just involve my typing in literally every single x value that I want? And the answer, as you probably either know or are predicting, is yes. And there are two functions in Numpy that will do this for us, or that do similar thing, that do similar things. One is called linspace, and one is called arange. So let me just do the linspace first. So I'm going to do np.linspace. Okay, so what does linspace do? It's a function that takes in 3 arguments. It takes in a starting value, which is going to be -2 for us because we are starting at -2. It takes in an ending value, which is 2, so we're going to put 2 there. And then it takes the number of points that we want there to be between -2 and 2. So let's say we want to do just like 100 points from -2 to 2. This is going to give us 100 evenly spaced points from -2 to 2. Okay, so now I'm going to run this code. Actually, let me come down here. Let's just see what this is going to give us first. So let's run this code, and then let's look at x. So if we run this, we should get something like -2, then -1.95, I guess, something like that. Okay, so -2, -1.95. Okay, yeah. So there's 100 going from -2 to 2. Maybe if I do 101. Yeah. Okay. At any rate, it gives us 100. This gives us 101 evenly spaced points going from -2 to 2. This here, let me just write this up here. This gives us 100 evenly spaced points going from -2 to 2, and then this would give us 99 evenly spaced points going from -2 to 2. Okay, and so we don't actually have to write out all of the points. We just have it in this vector. The Python does it for us automatically. Okay, and so now what's going to happen? Y, so I have a new x here. Y is just going to be sign applied to every one of the elements in the array x. That's what it was before. I didn't mention it explicitly, but we're just, we're doing y is equal to np.sign of x. It's going to look at every entry in x, do sign of that, and that's going to be our y list. So we have a set of x points. The y points is going to be sign of pi times the x points. Okay. So now if I plot this, actually let's make it 10. Okay, so if I plot this, this will look a little more like the sine function. So if I run this, I'll get something that looks a little more like a sine function, but still very angular. Okay, so very angular sine function here, because again, we're just doing all of the line segments in between the points. So like this corresponds to a point on the sine graph, this corresponds to a point on the sine graph, and so on and so forth. But if I do 100, my guess is that this is going to look much more like a sine graph. Okay, I mean, this is hardly, you can't really even tell that this is made up of a sequence of line segments because it's so fine. And then if we do 1,000, we're also going to get something similar. Kind of looks just like the 100 version though. So, okay, so this is one way to accomplish what we want to do. The other Python, the other NumPy function that's very similar to linspace is called arange. And for arange, I'm going to say x is equal to np.arange, A-R-A-N-G-E. And for this one, what you give is a start value, a stop value, and then the step size. So you give it a stop value, which is -2, a stop value, which is 2, and then a step size, which I'll do 0.1. Okay, now one important thing about this will go from 0.2 in increments of 0.1 up until 2, so it will not include 2. So I'm going to run this, and then we'll have it, we'll have it print x, and what it's going to be is 0.1, -1.9, -1.8, all the way up to 1.8, 1.9, but 2 will not be included here. So if I run this, this is what we get, and notice -1.9 is the last entry, not 2. So if you want to include 2, you have to add the step value, 0.1. So if we run this, this does include 2. Okay, now the problem here is oftentimes when we're doing programming, we might want to change the step value. So if I change the step value here, I have to make sure I change it there. And so instead of doing it like that, it's a little bit better to just give this a variable name. Step is equal to 0.1. This is going to be 2 plus step, and we run the code. Again, get the same exact thing. But now let's say I want to change the step size to 0.05. If I run this again, it's going to go from -2 all the way up to 2. All right, and so this is what we get here. And then also if we change it to like an odd step size, so odd meaning like if I just do 0.03, this is like the last one is not going to land exactly on 2. So let's see what we run when we get this. Okay, we actually go up to 2.02 because I have my step size. 2 plus step would be 2.03, so it gets the very last one, 2.02. Okay, if you don't want to include that, you could just delete this, and we're going to have all the way up to 1.99. Okay, so these are various things that you could do. If I come up here and say this is equal to a range -2, 2, I'll say 0.01. Okay, so I'm doing my step sizes of 0.01, and I run this. Okay, this is what I get. And technically, it doesn't include this very last point at 2, 0. But it's so close it actually looks like it. But if I were to make my step size 0.5, we would get something that doesn't really look like what we want it to look like. Okay, right here, because notice it goes up from -2 to 2, not including 2 in 0.5 increments. So it doesn't get to 2. If I do 0.25, it'll go up to 1.75, and so on and so forth. Okay, so I think like this right here, I think this right here already gives you like some really good ideas on how to do some graphing. In the next video, what I want to do is I want to show how we can have different figures. Actually, I think in the next video, I want to show how we can label the axes and do some different things. And then in the next video, I actually want to show how we can have like different graphs in the same figure. So maybe here you want a quadratic function, here you want a cubic function, here you want a sine function, here you want a cosine function, that sort of thing. So that's what we'll look at in the upcoming video.